I want to talk about equilibrium. Okay, equilibrium means different things in different sciences and with different people and how they talk. You know, like maybe you have equilibrium in your relationship with that significant someone, you know. That means that everything's good, you know, there's give and there's take and you're working things out. You're in equilibrium. Maybe emotionally you're in equilibrium, you know, everything's good. You're not veering off into insanity or anything like that. In chemistry, they have, you know, chemical equilibrium. That means the products and the reactants, they're kind of going in both directions and things are good. Everything's steady. Well, in physics, what we mean by equilibrium is this. Acceleration is zero. There is no acceleration, which means that the velocity is what? Constant. Now, is zero a constant? Could you have something at rest and it's staying at rest? Yeah, that's a constant velocity of zero. So if something is at rest and remaining at rest, or if something is in motion and remaining in motion, it's in equilibrium. Which means that well, what's net force equal to? The net force equals ma, but if the a is zero, then the net force must be zero. And the net force is what you get when you sum all the forces acting on an object. When you add up all the forces acting on an object, if they all cancel out, they have to be equal to zero as well. Okay, so that's what equilibrium means. So when I say something is in equilibrium, what I'm saying is the object is not accelerating. It's either at rest or it's moving with constant velocity. The net force is zero. And when I add all the forces together, I get zero. So that's what I mean by equilibrium. Now, what if I had an object that looked like that? Let's suppose there's just a ring. So let me draw a ring. And I can hook forces onto this ring. I can just pull on it. Maybe I tie 3 different strings to this. We're actually going to be doing this in a lab on Friday. But suppose I have a force pulling on it to the right, like this. And suppose I have a smaller force. We'll call this F1. And then I have F2 pulling on it up like this. Now, these two forces, what are they trying to do? They're going to make this ring go like what? I mean, if I add these forces together, I would get the net force. And I think you would see that this object would try to accelerate in that direction, wouldn't it? That's what I get when I get F1 plus F2 tries to make it go like this. So what if I wanted to hold this ring in equilibrium? What would I do?
The one on the other side of F1.
Yeah, I would just cancel these two forces out by applying a force like this. That's just opposite of this. Now, what we call this, the force I get when I add these two together, is called the resultant force. And if I just take the resultant force and add 180 degrees to it and cancel out that resultant force, I get the force that holds that object in equilibrium. It keeps it from accelerating. And this force right here is called the equilibrant force. So this, when I add F1 and F2 together, I get Fr, which is the resultant force. And then when I want to cancel out that resultant force so that to keep the object in equilibrium, that's called the equilibrant force, sometimes called F sub E. Okay. Now, the book goes into this in a little bit more than I'm going to. I don't really care that much about the equilibrium force and what I'm going to be teaching you guys, because in the real world, you don't really think of things like the equilibrium force. What you do is you look at objects, you look at the forces on the object, you ask yourself, is that object in equilibrium? If it is, that means when you add up all the forces, you get 0. And then you're going to have to solve for some unknown force. Okay, that's all there is to it. So it's not that big a deal. But the book does talk about resultant forces and then equilibrium forces. And it's just the resultant force plus 180 degrees to the angle of it, and you've got it. Okay? Well, let's talk about this problem right here. What if I gave you these two forces? In fact, let's turn this into an example. What if this was equal to 20 newtons? And what if F2 is equal to 10 newtons? And this is some unknown force. The equilibrium force, I'm just going to call it F3 though. And what if this is what's given, and you're trying to find, okay, what is F3? What is the magnitude of F3 and what is its angle to keep this in equilibrium? Okay, well, we would use the procedure. Now, I've already done or given, find, and solve, sort of. I kind of combined step 1 and step 2 of the procedure, right? Here's what's given, and it's on a free body diagram already. I drew what was given on the free body diagram. So let's go right to step 3. Okay. Now, what does step 3 say to do? And this is for Cody Curtin. What is step 3? Well, step 3 says to identify your x and y axis. So here's step 3. We're going to modify step 3. Step 3 says to draw your xy axis. Okay. But then what we have to do is take the forces and show forces with x and y components. Okay, because this is what's really different about this section than what we did in the last unit. In this section, we're going to have forces that aren't aligned with the x and y axis. And so what we have to do is break them up into their x and y components. So for this problem, I'm just going to say, okay, let's let the horizontal be our x and the vertical here be our y. So this is x and this is y. But now I'm going to show you how to break them up into their components. So watch very carefully. Look at F1. What direction is F1 in? It's in the x direction. It doesn't have any y component, so we don't need to bother with it. It's already broken up into its x and y components because it's all in the x. And the same is true with F2. It's all in the y direction. But what about F3? Well, F3 is tilted down like this, isn't it? So let me show you what to do. We're just going to make a right triangle out of it. Watch. And I have to do it with dashed lines.
Hi, we'll try any books?
No books today. We just got started on it today. Okay, so here's what I'm going to do. Here's my force that's on my free body diagram that is not lined up with the x and y axis. So what do? I'm going to show its x component and its y component. We dealt with components before. So I'm going to call this F3x and F3y. Okay? Any questions on what I just did? See, this is all in the x direction, this is all in the y direction, but look at F3. It pulls down and it pulls to the left. It does both at the same time. So I'm going to break this up into its components. Now when I do step 4 of the procedure, I can, let's sum the forces in the x direction, and that will equal ma in the x direction. A little bit. Okay, so now it's given that this force F3 is keeping this thing in equilibrium. So the object is in equilibrium. What does that mean about the acceleration? The acceleration is equal to 0. So we know that this is going to be equal to 0. A is 0, so it's just 0. Now let's look in the x direction. Look at the x direction on my free body diagram. What have I got? Well, in the x direction, I've got F1 is how much? 20 newtons in the positive direction. Now, what is true about F3 in the x? It's in the negative direction, isn't it? So I'm just going to put minus F3 in the x is equal to 0. So this will give me the max. Now, what does this tell me? If 20 newtons minus F3 in the x is equal to 0, what is true about F3 in the x direction? It's equal to 20 newtons. And by the way, what direction is it in? It's to the left. Now, which normally means I would put a negative sign here, but I already put the negative in there. But let's just stipulate, hey, I know it's to the left. Okay? Now, let's sum the forces in the y direction equals ma in the y direction. So I'm just following the procedure here. And in the y direction, what have I got? Well, in the positive y direction, I've got F2. I've got 10 newtons. And then anything else in the y direction on my free body diagram? Oh, look at that. F3 in the y. See this force right here? It's pulling down by this much, minus F3 in the y. Now the object is in equilibrium, so what is true about the acceleration in the y direction? It's 0. And so now I've got F3 in the y direction is equal to 10 newtons. Now, of course, it's down, but, we can figure that out. Now we want to know, what is F3 and what is its angle? Well, I know its x component and I know its y component. So how do I figure out how big the vector is? What do I use when I know the x component of a vector and I know its y component? I use Pythagorean Theorem. So F3 is going to be equal to the square root of its x component, 20 newtons squared, plus 10 newtons squared. Okay. And what do I get? Well, this is 400 plus 100. It's the square root of 500. So where's my square root button? So square root of 500, 22.4. That's the magnitude. Now what's the angle of this guy? Well, let's figure out what this angle is right here. Take the inverse tangent, theta, is equal to the inverse tangent of what? Let me zoom in. You guys probably can't see it in the back, can you? You can? Okay. I'll zoom in a little bit. Well, it's the inverse tangent of the y over the x. Now the y value is, what was it, 10 newtons? Over the x value is 20 newtons. Newtons cancel, of course. And so the inverse tangent of 10 divided by 20, or 1/2, And you get, oh, that's interesting, 26.6. Now, so that means that this angle right here is 26.6, and that makes sense, doesn't it? But what is it actually? What is, if I was going to use polar coordinates, what would I have to do to measure this angle from here all the way over like that? I would have to do what? Add 180 degrees to it. So plus 180 equals, so F3 is equal to 22.4 newtons, and at an angle of 206.6 degrees. And that's my answer. That's, if this is 20 newtons and this is 10 newtons and you want to apply a force to keep it in equilibrium, that force will be 22.4 newtons in magnitude at an angle of 206 degrees from the positive x direction. Now, if you listed the answer as just being 26.6 degrees, as long as you show it in the picture where that angle is measured from, I'd probably give it to you. Okay? So, here's what I want you to do now. I want you to do this example problem from the book, and I want you to use the procedure to do it. So here's the example problem, and by the way, this is part of the homework here, so this is E1. It says, oh, don't look at the answer, okay? And by the way, I do not like the book solution. So let's zoom in. And it says, a 168 Newton sine, here's a sine, is supported in a motionless position by two ropes that each make 22.5 degrees with the horizontal. What is the tension in the ropes? Well, now this is a very real world kind of problem, you guys. My son Aaron is a civil engineering major at Fresno State right now. He's really enjoying it. And one of the things civil engineers have to do is hang signs. Just one of many things that they have to do. Like if you're going to have, like a city, you're going to have to hang a big sign, or maybe you're working for a business and you're going to hang a sign, and you're going to hang it by a rope. Now this sign is pretty heavy. So what's, you don't want to use thread, right, to hang this sign, because what'll happen? It'll snap. But you also don't want to use big, thick, 4-inch diameter cable to hang this sign either. Why? Because it's so expensive. So here's what you want to do. As a civil engineer, and all engineers, this is a great definition for what engineering is. You're going to use the laws of science and nature, physics, to solve the problem at the lowest possible cost. That's what engineers do. They solve problems using the laws of nature at the lowest possible cost. So what we want to know is how much force is going to be in that rope to hang that sign at this angle, and what kind of rope am I going to need? Then you can look it up in a catalog or something and order it online or whatever. I mean, that's what you're going to do as an engineer, is you're going to order what you need with an adequate safety margin and all that. Okay? So, here's the problem. Now, I'm going to do step one for you here. So, here's what's given. Okay, we've got a sign. And this sign has a weight. mg is equal to 168 newtons. And we've got a rope, two ropes that are tied to the top of this thing, and they're at symmetrical angles of 22.5 degrees. 22.5 degrees, like that. And we want to know what is the force in these ropes. So we'll call this F1 and this F2. So we want to solve for F1 and F2. So find F1 and F2. Now, so let's solve. Now this is a complicated problem. It looks fairly simple, but you have to go through a fairly rigorous process. Now I'm going to give you about the next 5 minutes. I want you to do this on your own. Don't look at the solution in the book. Try to do this. Use the procedure. We just did step 1. Do step 2, 3, and 4, and 5 to solve for F1 and F2. It involves a little bit of algebra. The book's answer is correct, so you can check your answer with that when you're done. Okay? So try to make that happen.